So for a single standard addition, what we're essentially doing is measuring a diluted sample, and then the standard addition is a diluted sample plus some known volume of a known concentration of the analyte, which is the spike. So that's the standard addition. So in this case, let's use an example. We're measuring manganese in steel, so we're going to convert it to permanganate and do some absorption spectrometry. So we'll take 7 milliliters of our sample. So this is our V0. And then we'll make it up to a total volume of 10 milliliters. So that's our VF, final volume. And the concentration of the analyte in the sample is what we're trying to find, that's Ca. Now for our spike solution, our standard addition, we're going to take the same volume of analyte, same volume of sample, so it's 7 milliliters. We're going to make it up to the same volume, so that's 10 milliliters. But we're going to add this known concentration of analyte, the spike. We're going to add just 0.01 milliliters. So now we have the same concentration of analyte, the same volumes, but we have this spike solution, and that has a known concentration. So in this case, we're going to say 1,000 milligrams per liter. Okay, and we're going to measure both solutions. So the signal of the sample is measured to be 0.542, and that's in absorbance units. And the signal for the spike solution is 0.762. So now we have everything we need in order to solve for the concentration of the analyte. And remember, this is the concentration of the analyte in this sample solution, not in the diluted solution. So we're going to plug those numbers into the equation, and the equation we're going to use says that the signal from the sample divided by concentration of the analyte, which is what we're trying to solve for, over V0, volume of the sample over the final, or the total volume, equals the signal for the spike divided by concentration of the analyte times V0 over Vf plus concentration of the spike times Vs, the volume of the spike, over the final volume. Okay, now we can plug some numbers into this. So our sample absorbance was 0.542. Ca we don't know. We're going to end up with Ca in two places, but we can deal with that. We had 7 milliliters over 10 milliliters. Again, the volumes, the units have to be consistent. So if we're going to use volumes, we'll use milliliters. We'll use milliliters for every volume. Signal for the spike was 0.762. Ca over 7 multiplied by 7 over 10, and this is 1,000 milligrams per liter, so this will give us an answer in milligrams per liter, 0.01 over 10. And when we actually do some of those calculations and simplify it a bit, this is going to be 0.7 times Ca. This is also 0.7 times Ca. This term here ends up being equal to 1, so that simplifies. So we get 0.7 Ca plus 1. Now we just rearrange, it's just math, so we're going to take this term and multiply it by 0.762, and then we're going to take this whole expression and multiply it by 0.542, and when you do that, we end up with 0.3794 Ca plus 0.542, and that's equal to 0.5334 times Ca. So then we just subtract 0.3794 from 0.5334. We're going to swap it around so we get Ca on the left hand side, and that gives us 0.154 Ca is equal to 0.512, and then just divide through. We get that the value, the concentration of the analyte is 3.52, and that's in milligrams per liter. And it's worth remembering that is the concentration of the analyte in the sample solution. So usually we would have to convert that back to the concentration in the actual sample itself. So you would figure out milligrams and divide it by the mass of the sample.